Hello everyone. We want to discuss polar derivatives now, derivatives of polar graphs. Now we know from parameterization that if I have x of t and y of t, then dy dx is just dy dt over dx dt. We've already established that previously. Now for polar coordinates, x equals r cos theta and y equals r sine theta, but if we think of r actually as a function of theta, then x and y ultimately are functions of theta. So using the same reasoning, if I said then what's dx d theta, and I just simply use the product rule, so the first times the derivative of the second would be negative r sine theta, and then the second times the derivative of the first, I'll write it in this order, dr d theta cos theta. Similarly, dy d theta, which would be first times derivative of the second, plus the second times the derivative of the first, and then dy dx would simply be dy d theta over dx d theta because we are using this particular parameterization. This gives the finished form for all polar derivatives as being this following scary looking quotient. So let's consider the cardioid r equals 2 minus 2 cosine theta, which looks like this. I would like to find the derivative at every point on there in the xy plane, but in the r and theta terms. So to start with, let's find dr d theta, which in this case would be simply 2 sine theta. Now all I need to do is substitute this quantity everywhere I see the r, and this quantity everywhere I see the dr d theta. So dy dx would simply be then 2 minus 2 cos theta times cos theta plus 2 sine theta times sine theta over the negative of 2 minus 2 cos theta sine theta plus 2 sine theta times cos theta. So if I distribute and I combine terms, then my numerator reduces all the way down to 2 times the cosine of theta minus 2 times the cosine of 2 theta if I apply a double angle formula. And my denominator, negative 2 times the sine of theta plus 2 times the sine of 2 theta. So for every value of theta between 0 and 2 pi, I can plug them in there and I can find the derivative. Now continuing with this same function, I would like to find the slope of the tangent line at these 3 different values of theta. So if I plug those in one at a time, then the proper notation would be theta equal pi over 2. Now some of these are very simple to evaluate. Pi over 2 is very easy because the cosine function will be 0 and the sine function will be 1. So my numerator here is simply going to be, on top I'm going to have a 2, on the bottom I'm going to have a negative 2, and I get a slope of negative 1. Now if I look at my graph, pi over 2 is right here. That means that at that point I have a slope of negative 1, which is pretty accurate according to my picture. Now let's consider dy dx at the value of theta equals 2 pi over 3. Now, in this case, I'm going to get a lot of root 3 over 2's and potentially 1/2. So after I plugged all those in and evaluated, it turns out my numerator ends up being 0. So that slope is actually 0, which is strange. So where is 2 pi over 3 on my graph? Well, 0, pi, 2 pi over 3 would be about right there, or in other words, right where I have the horizontal tangent. Let's see, right there. So again, very accurate according to my picture. And finally, let's consider dy dx when theta is pi. And again, that should be relatively simple because the cosine of pi is negative 1, the cosine of 2 pi is positive 1, the sine of pi is 0, the sine of 2 pi is 0. So we get a 0 in the denominator this time. Uh-oh, this slope is undefined. But the only way we can have an undefined slope is if I have a vertical line.